So in this weekly video, we're going to talk about a couple of things about chain rule problems, and then I also wanted to mention a typo in worksheet 5, and I believe you've already done this actually last week, but on problem number 7, it should have been tangent of x, not tangent of x prime. So if you were confused about that, you might want to go back and take a look at that. But this week you'll be learning a new rule called the chain rule. And the chain rule we'll talk about here in just a moment. Okay, so the chain rule is used for composite functions. So remember from Algebra 2 and from pre-calculus that a composite function is a function where you are plugging one function rule into another function rule. So let me give you some examples of what this might look like. My tablet is not working, so I'm going to have to write this using the mouse pad, so this might be a little bit messy here. But for example, if you took the function x cubed and plugged it into, let me think for a minute. Actually, let's do x cubed plus 1. And if you plugged that function into the square root function, that would be a composite function. You could plug 2x to the 4th into the sine function. That would be a composite function. So it's when one function rule gets plugged into another function rule, there is a specific process we have to use to find the derivative, and that's called the chain rule. So you'll be using the chain rule on composite functions. Here they define these composite functions for you, and they tell you that h of x is what you get when you plug g of x into the function f. And then s of x is what you get when you plug f of x into the function g. And so they want you to find each derivative if it exists, and if it doesn't exist, they want you to explain why. So let's clarify here that this is, let's see, a little bit hard to see. So this is function f. This is function g right here. And then this, and I'll move this arrow in a minute, I had added that in for something else. This is function g over here, this kind of gray function, and then this is function f. So let me grab this. Okay, so the chain rule is going to tell you that in order to find the derivative of a composite function, so remember h of x here is defined as this composite function. So in order to find the derivative of that composite function, you take the derivative of the outside function. So f is the outside function. We do f prime of g of x. And you'll be learning this in the unit this week. So if this doesn't make sense, you'll get more instruction on this later on. But this is really mainly how to solve these specific problems. And then you multiply that by the derivative of the inside piece. So you do the derivative of the outside piece with the same function being put in as it was originally. And then you multiply that by the derivative of the inside function. Same thing then for s prime of x. You take the derivative of the outside function with the same thing being plugged inside as it was up here, and then you multiply that by the derivative of the inside function. So if I remember correctly, you are doing problem number 110 on your assignment. So let's take a look at how we would do that. In this case, we'll actually be using this one right here because I think, because that pertains to, oh, no, actually we'll have to use both of them, won't we? I thought it was going to use just s, but it's going to use h as well. Okay, so in order to find h prime of 3, here's what we need to do. We're going to use this chain rule right here, and what I've done down here is I've started to show what you would get when you're plugging in this specific 3 for the x. So instead of h prime of x, we're going to put h prime of 3, and the reason we're doing that is because they're giving us 3 for the x value. So I'm basically replacing every x here with a 3. So that's what I have here. And again, this is just applying the chain rule that you'll learn about this week. And I think actually that might be it. Let's see. Well, not it, but I wanted to see if there was anything else I had. Oh. Okay. So let me show you where I got these things from here. Okay, so the first thing I want to do is I want to figure out what g of 3 is. So I'm going to use my graph, and here's my arrow. G, this is the function g. I'm going to find g of 3. Well, here's 3. And, oh, whoops, I'm on the wrong one. Sorry, on this one. Okay, here's g of 3 right there. So if I plug in the value 3 into the function g, I come over here and I get a value of 5, and that's where I got this from. So I'm plugging the 5 in for g of 3, because if I plug 3 into the function g, I get 5. And then basically I left the rest of this stuff the same here, and I will be figuring out those things here in just a moment. So now I found the g of 3, that's the easiest thing to find. Now I need to find f prime of 5 and g prime of 3. So I'm going to use the graphs, and remember that this prime notation here is basically the notation for the derivative. And remember that the derivative of a function at a point is the slope at that point. So let's come up here and, oops, I keep going back to the wrong graph. And let's look at the slope of function f at the input of 5. So here's the 5. Here's function f. And we want to find the slope of the function at that point. Well, fortunately, this is a nice straight line. So I'm just going to find the slope by doing rise over run. The slope of this line will be consistent everywhere on the line. So basically I'm going to go, I'm going to find the slope between this point here and this point here by going up 2 and over 1, 2, 3, 4. So that would be a slope of 1/2, I believe. Let's see if that's what I have here. Okay, so the slope of the function f at the point 5, and I remember I got the 5 by plugging it in for g of 3, is 1/2. Now I need to find g prime of 3. And by the way, I have this little icon here. This guy is my slope guy. So we just found the slope at that point because that's what f prime of 5 means. So now g prime of 3 means that we go to our function g, which is the gray function, for an input of 3, and we find the slope right there. So I'm going to move my slope guy up there. And the slope there is going to be, it looks like from there it's up 1 over 1. So I think that g prime of 3, the slope of function g at the x value of 3, will be 1. And so when I simplify this, I get 1/2 times 1. That gives me 1/2 for this entire expression here. If I do the same thing for s prime of 9, which is this, the derivative of s at 9. Again, s is a composite function, so I have to use the chain rule. The chain rule is defined here. You'll learn more about it in the materials section this week. So basically I'm going to start by plugging a 9 in for all of these x values, and that should be what I have here. So I have g prime of f of 9 times f prime of 9. So I'm basically just plugging a 9 in for all of these x values. Then, the first thing I'm going to do is I'm going to find f of 9. That's the easiest thing to find. So I'm going to come to my f function here, and I'm going to go to an input of 9. And if I come up here, that seems to be 8, I believe. So I'm going to plug 8 in for f of 9. I'm going to have g prime of 8 times f prime of 9. Now I need to find these derivatives, and again, a derivative is really a slope. So I'm going to come to my g function and find the slope at 8. So the gray function is the g function. I come over here to an input of 8. If I come up here, the slope seems to be down 1 over 1, so that should be negative 1. And now I need to find f prime of 9, the slope of function f at the input value of 9. If I come over here to 9, and I come up here, that seems to be up 2 over 1. So I think that's a slope of 2. Negative 1 times 2 is negative 2. That means that this entire process for the chain rule gives me negative 2 as the derivative of function s at the point 9. So you will be doing that on your homework. You'll also be applying the chain rule in some other ways, but you'll learn more about those ways in the materials, and I thought they were a little bit more clear how you would do those than this one was. I also wanted to talk a little bit about the next topic that you'll be talking about, which is called related. So I have some information on related rates to go over with you, but you'll be doing the first worksheet on related rates this week, and the information that I had that I wanted to go over is actually from worksheet 2. So what I wanted to do instead, I'll save this for next week when you actually do worksheet 2, I wanted to go over a website that I'm going to link for you so that you can see how to do some of these related rate problems. So I will attach this link to a Schoology message as well as to the updates, which is probably how you're watching this video. But this is going to be to a site called Math Scoop. And this site is really helpful for this concept of related rates. It identifies several steps that you'll use for these problems, and they're pretty complex problems, so it's really nice to have this series of steps that mirrors what you'll be learning in the materials this week as well. But then it has some sample problems, and it walks you through what those steps would look like for the sample problems. So let me just kind of walk you through this particular problem. So again, you'll be learning more about what related rates are as you go through the materials, but this problem 1 talks about a circular shield of bronze, and when it's heated over a fire, the radius increases at the rate of 1/5 of a centimeter per second. The question you're answering is, at what rate is the shield's area increasing when the radius is 50 centimeters? So you have a lot of things going on here and a lot of pieces to pull out of this. So the first thing you want to do is you want to draw a picture. And I apologize, I think my internet is really slow today, so this may not work quite the way I want it to, but so here's the bronze shield. The radius is increasing and the area is too. We want to know at what rate the shield's area is increasing when this radius is 50. So this gives you a good picture of kind of to start off with. Then you want to identify what you're looking for. What you're looking for is the rate of change of the shield's area when the radius is 50. Well, rate of change is a derivative, so we're looking for how is the area changing over time when the radius is 50. So this notation is the rate of change of the area as time is changing, and you'll learn more about that in the materials section as well. You want to identify the givens. You know that the radius is 50. They tell us that in the problem right here. They also tell us that the rate of change of the radius is 1/5 of a centimeter per second. So that is written down here in kind of math terms. The rate of change of the radius over time, so dr dt, is equal to 1/5. The radius is changing over time at a rate of 1/5 of a centimeter per second. You want to identify the equation that relates these variables. Well, what we're trying to accomplish is finding the rate of change of the area, and the area formula for a circle will relate the radius to the area, obviously. So we want to use area equals, sorry, getting some words stuck here, equals pi r squared. You want to take the derivative of this, and you'll be learning about something called implicit differentiation. So right now this may not make a lot of sense, but this week you'll learn about this. We take the derivative of the area over time, and then we use the product rule to take, and implicit differentiation to take the derivative of this side. So you bring the 2 down in front, you get 2 times pi times r, and you'll learn about where this dr dt is coming from. And then you want to substitute what you are given here and here into that equation. So you'll be substituting the 50 for the r and the 1/5 for the dr dt. And then sometimes you have to find other variables, but in this case that doesn't apply. You'll solve, and so when you do 2 times pi times 50 times 1/5, you get 20 pi. This is a rate of change for the area, and I believe they have the units wrong on this. The area should be changing at a rate of 20 pi centimeters squared per second. So I believe they are missing a unit of a squared centimeters here in this case. But then there's another problem, and you can walk through the same thing. It'll have you draw the picture, and you can kind of get an idea of what that looks like as the change is happening. Here's another good one about a ladder problem. You'll be learning more about a ladder problem this week. Again, same kind of thing. You can click on this and see how this problem is set up kind of in motion, and then it will walk you through these kinds of steps. So hopefully this site will be helpful as you solve these related rate problems. You will also be doing some I know you'll be doing some cone kinds of problems as well. I think you'll probably be doing some cylinder problems and maybe some sphere problems, but I've seen some cone examples in there as well, so this would be another good one to take a look at. And you might want to look for problems that are similar to the problems you will be doing as you kind of glance through here. That would be a helpful thing to kind of guide you through the steps you'll be taking on those problems. So if you have questions on related rates, let me know. I will link this site to both the updates and to the Schoology message.